Good afternoon, ladies and gentlemen. My name is Alexander and welcome to the webinar. Thank you for joining us today. We prepared for you today a study of board input possibilities to the circle plate, and we will tell you new tips for the stiffness analysis. All of you can see the control panel. There can be entered questions anytime. Please don't hesitate and ask anytime. We will do our best to answer during the webinar. Unresponded questions will be answered by email after the webinar. My name is Alexander Shodkovsky and my colleague is Vít Hulčík. We are both product engineers and we will guide you through the webinar today. And we will start right away with the examples, and I will pass to my colleague, Vít Hulčík.
Good afternoon once again. Thank you for the word, Alexander. The first example is designed as the study of the board's input for possibilities for the circle and plate of a joint from Jakarta velodrome, which was designed and checked by the Idea Statica connections. It was this circle and plate between members, and it was placed here at the construction steel frame. We were inspired by one of our users, which had an issue with defining the group of bolts in right position. We will walk through several possible solutions together. Let's jump right into the application. We have to define load and manufacturing operations. Just give me a second. I will import the load from the Excel spreadsheet. Great. Let's prepare the design. We can choose end plate or plate-to-plate manufacturing operation and define parameters. It will be a circle one with certain radius. And with 8 bolts. I want to make it more stiff, so let's add a ribs. Their thickness will be 10 millimeters, and they will have a certain geometry. I want to have 4 ribs through all circle. And let's copy this manufacturing operation and adjust it to the right position. Great, we have done. You can see that our bolts are overlapped with the ribs. I don't like it. So the first thing, we can change the radial position of the ribs. Let's start at 22.5 degrees. That's one possible solution, but I don't like it because the direction of the load is not in alignment with the direction of the ribs. So let's do another solution. I will set the radial position to 0 again, and let's go back to the plate-to-plate manufacturing operation, and we can persuade this manufacturing operation to input 0 bolts simply by typing 0 here. which is great because we can now define another manufacturing operation, bolt grid. And one important remark, we have to change the coordinate system to polar one. And we can start with the definition of the angles for bolts. The tooltip can help you. We can define the position for the bolts in several ways. The difference is in the usage of separator between the angle values. The separator can be space or semicolon. Let's start with the space. I will type in 22.5, which is our first ball starting position. And simply I can use a space bar and type another 22.5, which gives me a relative position for the second bolt relatively to the first one. Let's type another one, another relative position to the previous bolt, another 22.5 degrees. Next will be relatively 45 degrees. Great. And I can continue with 2 22.5, which gives me a full group for first and second quadrant. Now let me just finish with the third quadrant and with the fourth quadrant. Great. We have all circle. As you can see, some values are repetitive. So let's just shorten this input. I can type 22.5 multiplied by 3, and I can shorten this 22.5 multiplied by 2. And if I use this input 2 times, the result is the same, but we used multiplying. That's the first possible solution with the space between the values. Let's use the semicolon. If we use semicolon, we will enter the angle values absolutely to the origin of coordinates, which is 0. Okay, we can start in the same way, 22.5, but I will use the semicolon, and now 45, which is for the second bolt, and again semicolon and 67.5. That's the third one. And I can type another bolt, for example, 90 plus 22.5, which is 112.5. And I can go on. We can combine these two solutions. So I can type in 22.5 multiplied by 3. Oh, sorry, 22.5 multiplied by 3. 112.5. Second quadrant, and another one. And the last quadrant will be multiplied by 2. Great. Let's check our detail by stress-strain analysis. Well, we have the design and the check, and our detail passed the code check for the stress-strain analysis, and we will jump into the check, and let's see the bolt forces. You can see bolts in the first and second quadrant are utilized, bolts in third and fourth not. So what do you think if we skip the middle ones in the third and fourth quadrant? How we can do that? So just combine what we already know. 22.5 multiplied by 3, 45, 22.5 multiplied by 2. And now we want to skip the middle ones. So let's just type in 45 multiplied by 4. And we have another bolt group here with skipped middle ones. Let's check this designed joint by stress strain analysis once again. Great. Our detail just passed the code check. This is the end of the first example, and we will jump right back into the presentation. We will continue with the theoretical background for the tips for stiffness analysis. And my colleague Alexander will do for you demonstration later. For the classification, we are using the procedure from the Eurocode 1993-18, clause 5.2.2 and 5.2.2.5, the classification by stiffness and the classification boundaries. The joint can be classified as pinned, semi-rigid, and rigid. How we can do that? The analysis gives us dependence of the joint rotation on the bending moment, which is this green curve. The limit value of capacity of the connection for the 5% equivalent strain for the plates, 2/3 of this limit value, and the initial rotational stiffness or tangent rotational stiffness is defined like this. And for the level of the design load is the procedure same, and the result is the second rotational stiffness. The result values are provided in the result table, and you can calculate it by your own and check it. For the classification limit, semi-rigid and rigid are two options. For the frames, where the bracing system reduces the horizontal displacement by at least 80%, this is this one, the top one, and for the other frames, this bottom one. This choice can be defined at the code setup in the top ribbon and here in this checkbox. My colleague Alexander will show it later in the practical demonstration. In the Geometry tab, there will be another input box if the stiffness analysis is selected. You have to input the theoretical member length to define the length of member for direction Y and direction Z separately. And according to the clause 5.2.25, figure 5.4, the theoretical member length of analyzed member is the span of a beam from center of the column to the center of the column. By the usage of the beam link, we will get all selected load effects for the joint design. This approach is not suitable for the stiffness analysis. You can see that we have a lot of them. And trust me, you don't want to calculate in a stiffness analysis all these load effects. It will take a lot of time. We recommend to find the most extreme load effect combination for the 5% equivalent strain for the plates and delete all of the others. Afterwards, create a cookie of this extreme load effect combination, and we will change it a little bit. One combination will be in a way that in one load effect is only the bending moment my. In the second will be bending moment my with corresponding shear force z, and in the third load effect will be all other original forces like the imported one. Let's calculate the stiffness analysis only for these three load effects. It will save your time. Let's pass the word to my colleague Alexander.
So, thank you, Vít, for the theoretical background about the stiffness analysis. And we go to our example. I have prepared a steel frame structure without bracing system. You can see we have a distance between the columns in one direction about 10 meters, and in the second direction it is 6 meters. We have prepared the example in the SIA Engineer software, and we will export it to Idea Statica. So let's go to the calculation. We calculate the whole structure. Okay, and go to the export of the joint. First, we will define our joint, for example, this one. And go to the export. We select all classes and make the export. So you can see we have got all three members here with the loads. Here, remember, for example, here this number 70.2 my. It will be interesting in the next steps. To speed it up, we prepared a template and we will apply it to this joint. And you can see we have all bolts, plates, and welds in the right position. And now we can go to check and make the stress strain calculation. And in this same way, we can import the joints from other software like StatPro, RFM, Sub 2000, and other. You can see it goes past the calculation, so we will go through it very soon. Well, you can see we have all done, everything is green. And to decide what combination to use in our stiffness analysis, we go to the plates and look at the series load effects. It is here, this one, C0121. We go to the load effects, we can look at it. It is the, you can see it is the first one. So we go to the end and delete all except the first one. But not to forget, it's good to go first to the project item and the connection to make a copy of it and to check the box with stiffness analysis. So that's the first thing. We can go back to the load effects again. We will delete all others. So, and then we make a copy of the first one. Here in this one, we will delete all and leave there only the my. So, and the second one, so we have prepared the loads and go back again to the geometry. Here we decided to make the analysis for the beam B102. It is this one with the length of 10 meters. So we have to put the theoretical length from 6 to 10 meters in both directions. And again, oh, sorry, it was the wrong one. You have to do it in the B102 and click on Analyzed Member. So it's prepared also the geometry. Load effects are prepared, of course. And we can go to the check. And the very important thing, what you have to remember is go to the code setup and here to check or uncheck the braced system. So because our system is not braced, we will leave it as it is and we can start the calculation. And again, to speed it up, I have prepared already the calculation for you. First one, I will show you how it looks like if we are going through it with checked braced system. You can see it's here. We've got here the numbers for the rotational stiffness, and the classification of the joint is rigid. And the next one, here we have unchecked this braced system, and the result is here. You can see the classification of the joint is semi-rigid. That means that you have to change a little bit your structure in SIA Engineer and to put in the correct rotational stiffness. I personally would take this number 30.2 and I will put it into the SIA Engineer again. So we will go here, we will close it, go to the structure, select the beam, excuse me, so structure, go to the model data, hinge on beams, and we will change this thing from free to flexible and input the number 30.2 and make again the analysis for this joint. And and I will show you right now the results. And the results are here. So in the first part, we made the analysis, and we had the, as I showed you before, we had in the joint, we had the moment 70.2 kilonewton meters, and in the middle of the span, it was about 36 kilonewton meters. And when we added the rotational stiffness into the joint, right now we get another results. In the joint, we have only 63.10 kilonewton meters, and in the middle of the span, we have much more moment. We have 43.4 kilonewton meters. That means that you have, again, check the cross-section in the middle of the span. So it was the example how to use the rotational stiffness, and we can go further to your answers and questions. So we will look if we have some questions from you. I've got here one question. It's here. Can we calculate the stiffness in other direction than in local y? Of course we can. I can show it to you. Just a moment, please. You can see here we have the rotational stiffness. We have the rotational stiffness for my, also for mz, and here in this step you can see the axial stiffness. So you can decide which one you want to analyze and to use for your structure. So it was the one question, and the second, I have got another question that's here. Just a moment. Can we define several board groups on one plate? I would say this is the question for my colleague Viet, so I will change the presenter to him and he will explain it to you.
Thank you, Alexander, for a great demonstration, and I can react on that question of our customer or attendee, should I say, and we can show it here on our first example. Let me just adjust this input. Let's say we have this board group, and from some reason we need to define another one, for example, in the third quadrant. So it's really easy, just add another board group. It's without any restriction. You can have several load groups, several board groups in one plate. There is no restriction at all. So I can easily input 202.5 to 22.5 multiplied by 2, and I can, for example, have bolts only in the third quadrant. It's independent on the shape. So if you have some kind of complicated shape of the plate, you can add several bolt groups really without any restrictions. I hope this is enough for this question, and we can have just a quick look on the other one. We have one question from Mr. Andreakis, and I can read it. After reanalyzing the structure due to the modified rotation flexibility, we have to make also a new stiffness analysis in INEA with the new updated moment in the joint because the second stiffness will be different and so on. This can be understood as an iteration process, and it depends on your engineering judgment if you are satisfied with the project or not. From our point of view, we recommend to do maybe 1 or 2 iterations and find some kind of equilibrium. That will be a great idea. So let's proceed with the presentation. We want to ask you about filling a small survey, which will take you approximately only 30 seconds. It will pop up on you after the webinar, and it's about the future development of these webinars, so it's for you mainly. We are taking care of your opinion. Also, the recording will be available in at least maximum 3 days, and we will send it to you by an email, or it will be available on our homepage or at our YouTube channel. If you're not a user, you can ask for the trial version, which is free, at our homepage ideastatica.com. And don't forget, we have a resource center. Here at our homepage on the top resources, we have top Ideastatica Steel, and you can find there all tutorials, videos, frequently asked questions, and a lot of other materials for study. Next steel webinar will be on 7th of March 2019, and we will be glad if you will join us again. Thank you for your attention and have a nice day.
Thank you too. Bye.